In this video series, we will treat the complexities of chemical reaction engineering for complex reactions. First, we have to define what is a complex reaction. Then we will go through the algebra, matrix algebra, and the differential calculus of the analysis. Now, let me first write the reaction stoichiometry for methanol synthesis. Methanol synthesis, one of the reactions that define methanol synthesis is using syngas in a 2-to-1 stoichiometry to produce methanol. This is a very common reaction in chemical process industries. It is the largest scale, largest volume of chemical that is manufactured. One of the largest volume of the chemicals that is manufactured as commodity chemicals. We said that we start with a syngas. Syngas is a mixture of carbon monoxide and hydrogen. However, we have a carbon dioxide hydrogen reaction that accompany the methanol synthesis, and we form carbon monoxide and steam. And this reaction is known as a reverse water-gas shift. Water-gas shift, since it is reverse, it is the reverse water-gas shift. Now, when we add those two reactions up, the net reaction becomes carbon dioxide plus 3 hydrogens producing CH3OH plus H2O. Now you see, I generated the third reaction by adding the first two reactions together. So in a reaction network, only either two of those three are independent. The third one is obtained either through addition or subtraction of the two of them. So, independence of a reaction network is important when we are dealing with a complex reaction network. So, we have to make sure that they are independent. In a complex reaction network, there are issues that we term selectivity. That we term as selectivity. Selectivity means the selective production of one of the products in competition to the others. What should we do? How should we design our reactors to improve the selectivity? What type of reactor should we use? Should we use only one or more than one? What are the process parameters? And many more questions, but let us address them first. The independence question is easily answered by looking at the reaction network for a three-reaction system, we can see that only two of them are independent, as we mentioned earlier. The third one is derived based on the two. But if we are dealing with a large network of reactions, we have to use advanced tools of mathematics. The best tool to use, the most convenient tool to use, is to go to a software. In this course, I recommend using MATLAB to determine the rank of a tensor. All right, so I'm recommending MATLAB, which is a shorthand for Matrix Laboratory. And we are going to generate matrices of reaction stoichiometries, and we will base our designs on those matrices. So when we generate the stoichiometry matrix, we can check whether the rank of that matrix is consistent with the number of independent reactions. If the rank is less than the number of reactions that we wrote, obviously some of the reactions are derived reactions that can be derived by the addition or subtraction of some of the reactions that are present in the network. Now let us start generating our matrix, but let us first write this reaction network with simplified symbolic identifiers. And let's write these reactions in a more formal structure. So our reaction 1 is A plus 2B producing C, and D plus B producing A plus E. I selected the first two reactions. These reactions in algebraic notation can be written as minus A minus 2B plus C to be equal to 0. This can be written as minus D minus B plus A plus E equals 0. We can also write this as a summation nu ij times ai equals 0. The first I refers to the species. The J refers to reactions. So we have two reactions. We can write this as nu 1 1 A1 plus nu 2 1 A2 plus nu 3 1 A3. We have three components in this first reaction is equal to 0. Nu 1 1 is the stoichiometric coefficient of the first component in the first reaction. It is minus 1. So this is minus A1, component 1, nu 2 1, component 2 stoichiometric coefficient in the first reaction. This is minus 2, A2. A2 is B now, right? Plus nu3 1, it is C, its stoichiometric coefficient is 1, A3 equals 0. We can also write the second reaction in the same format. Now our reaction index is 2. This is reaction 2. Again, the same definition, general definition is valid. We are going to use different indices. Nu 2 1. Component 1 was A. Nu 2 1 is plus 1. A1, this is plus 1. Nu 2 2 component 2 is B. B has minus 1 as the reaction stoichiometry, A2. Nu 2 3, the third component is C, and we don't have it here. Let's just put it 0 times A3. Nu 2 nu 1 2, I'm sorry, nu 1 2, nu 2 2, nu 3 2 plus nu 4 2. Nu 4 2, our fourth component is A, B, C, D, minus 1, A4. Our fifth component is E plus A5, nu 4, 5, 2. Nu 5, 2 is equal to 0. So now we have matrix-friendly components, matrix-friendly stoichiometric coefficients. Now we are going to generate our matrix. Let's do that. So our reaction matrix is going to be nu ij, A1, which is A, A2, which is B, A3, which is C, A4, which is D, A5, which is E. So we have reaction 1 and reaction 2 here. And you will understand why I wrote it in this fashion. All right, A1, minus 1. A2, minus 2. A3, plus 1. A4, 0. A5, 0. The second reaction, A1 is plus 1. A2 is minus 1. A3 is 0. A4 is minus 1. And A5 is plus 1. Okay? So we have generated our nu ij matrix or nu ij tensor. So we have component vector. This row is the component vector, and this column is the reaction vector. Reaction 1, reaction 2, and so on and so forth. Now let us do the matrix multiplication of R1, R2 with this stoichiometric coefficient matrix. I will derive the first component. R1 multiplied by -1 minus R1, R2 multiplied by 1 plus R2. This is my first term. Let me just do a little bit of housekeeping. Okay, so my first term, I'm going to generate a vector space. My first term is minus R1 plus R2. This is my first term. This first term belongs to the A column. My second term is minus 2R1 minus R2. This belongs to the B column. My third term is R1 only. This belongs to the C column. My fourth term is minus R2. This belongs to the D column. And my fifth term is plus R2. This belongs to the E column. Now, when I did this matrix multiplication, what I generated was the net rate of reaction with respect to that component. This indeed R sub A. This is R sub B. This is R sub C. This is R sub D. And R sub E. Once we have a reaction network of independent reactions, we can establish the reaction stoichiometry matrix. We can have their independent rates of those reactions, and the matrix multiplication in this fashion gives us the rates of reactions with respect to that particular component. So this R1s and R2s are in the following form. R1 is equal to K1 times Ci to the power alpha I. And R2 is in the form of K2 pi summation over all species Ci to the beta I. And when I do that, I mean something like this. This is K1, Ca to the alpha 1, Cb to the alpha 2, and so on and so forth. We don't know alphas. We don't know whether those reactions are elementary. We don't know if there are other elementary independent steps that are hidden underneath that overall reaction layer. Similarly, this is K2, Ca to the beta 1, Cb to the beta 2, and so on and so forth. So when we are dealing with such complex situations, it is better to simplify them in broad contexts as multiplication operators, in summation operators, in clean and clear indexes, and represent them in matrix form as such. So once those rates in terms of RA, RB, RC, RD, and RE are rigorously written, independently defined, the engineering part will be easier to handle.